So if you haven't watched the video about electron donating groups looking at phenol, do that first before you watch this one. And this will help kind of continue that picture and our understanding a little bit better. So on the electron withdrawing group video, we talked about how if you have an atom next to the ring with a lone pair of electrons, that's a donating group. It can donate electrons via resonance. I didn't put the halogens up as an example, though. And the picture is actually a little bit more complicated than that. So both of these can do resonance. Right, and that should make sense just sort of visually, right? So a combination of all these conjugated pi electrons, so all the carbon atoms have pi bonds, and then this next door to that, an atom with lone pairs. Those lone pairs should be able to share electrons with that pi system. It's a conjugated system. They also have inductive withdrawal, though, right? So chlorine and oxygen are similar in electronegativity. They're both more electronegative than carbon, so this is a polar bond that's going to be pulling electrons away from that carbon as it's donating in through resonance as well, right? So you have resonance and inductive withdrawal. And if we combine these two things with phenol, overall we're saying that it's still activating. It makes these reactions go faster. It's an electron donating group, so it's donating more than it's withdrawing. So it's an electron donating group, and so it makes the reactions go better. So we have two different effects. They're competing with each other, but it seems like resonance must be winning, right? So if resonance is donating and the inductive is withdrawing, the resonance must be winning. So we've got that resonance effect, which is pretty strong. Right, we're dumping electrons into the ring through resonance, right? I'm making my arrows fat to emphasize that. I do have inductive withdrawal, so this is a more electronegative atom, so it should be sort of pulling electrons away at the same time, but the sharing through resonance is generally a stronger effect, right? So that electron donation through resonance donates electrons, pound for pound stronger than inductive withdrawal. So it outdoes it in this case. So then overall, you end up with a donating group, right? Our halogens mostly are considered electron withdrawers, right? So we've got resonance donation. We have inductive withdrawal. The inductive withdrawal shouldn't be too different. The electronegativities in chlorine and oxygen are pretty similar. So that must mean the resonance is weaker, and that's definitely the case. So what you end up with in our chlorine, our chlorobenzene here, is you have weak resonance donation plus the normal inductive withdrawal. That's going to end overall make this an electron withdrawing group. So we call that deactivating to electrophilic aromatic substitution, right? Because eventually we want to react with electrophiles, right? So these reactions are happening with something strongly positive. So the more negative our ring is, the better. The more electrons we pull out of that ring, the worse it's going to be. So that's not favorable for this chlorine to have the inductive withdrawal pulling the electrons away so strongly. So they don't look that different, though. So why is the resonance weaker in the chlorine? And a lot of that can come down to size and electron overlap. So for our benzene ring with our pi electrons going on throughout the ring, remember? So if we kind of imagine them as the original p orbitals where those electrons came from, of course they're all bonded now. They don't exist in those p orbitals anymore. But remember, carbon-chlorine generally, even with an sp2 carbon, it's going to be a longer bond because that chlorine atom is bigger, right? And its electrons are in the 3s, 3p orbitals. They're going to be larger orbitals compared to carbon. And our pi overlap then is not so good. And so the atoms that are larger, the chlorine, bromine, and iodine, they don't do resonance sharing that well, right? Because you generally have poor overlap, and that's going to lead to that weaker resonance donation, right? The sharing of the different sized orbitals, the more diffuse, larger orbital, and the smaller, more compact, it doesn't work that well. It's not the strongest bond. So that's similar to even just a sigma bond, say carbon-iodine. It's a longer bond. The orbitals don't overlap quite as nicely. You get a weaker, more breakable bond. Right here, even in resonance, that sort of comes true. Small and large atoms don't mix that well. So you get weak resonance with a good inductive withdrawal overall, making the halogens a withdrawing group. And that comes true with the halogens in general. Their withdrawing strength outcompetes their resonance donation, and overall they do withdraw electrons and slow these reactions down. As a side note though, because of that resonance though, they do behave a little bit similar to the other groups, and so even though they're all electron withdrawing groups, in general they're ortho para-directors. So in terms of just predicting where the reactions go, they push the reactions to happen into the ortho and para positions, just like the other donating groups that we looked at too. So that's our